So this is joint work with a number of people, two of whom are in the audience. I can see one, but Anish is also there. So Raghav and Anish are in the audience, and other people are William Hesse, Thomas Schwentek, and Thomas Zoime. This constitutes two papers. I'm going to talk about dynamic complexity of reachability and related problems. So I'm first going to give an informal introduction to what dynamic complexity is all about. The idea is, and I'm taking the example of reachability as a sample problem. So you have a graph. So in the static world, you are given a graph a priori, and you want to compute whether there is a path from S to T or not. That is, or you want to compute whether there is a perfect matching in the graph or not. Here you are given a graph which with edges coming in and going out, and you want to maintain the property that maintain a particular property like reachability. So for example, here you have S and T are two nodes, and at some point this is what the graph looks like. Now once this edge this edge breaks down, you can infer that the graph is, T is still reachable from S. Now another edge breaks down, and now what happens is that you can infer that S cannot reach T. And all the while we maintain some auxiliary database along with the original graph, which will tell us whether ST are reachable or not. So this is and again another edge is added. So for example, this edge is added here, and now you can see that there's a path from S to T again. The path from S to T is restored. Yeah. So why are we studying this very simple problem in this very simple setup? One reason is that there are some applications to database systems. Another reason is that you would expect that we don't have to recompute the entire result every time. So we know that reachability is NL complete, directed reachability is NL complete, and you would presumably need, you can't do better than that because it's NL complete. But in the dynamic setting, you can do much better than that. What was known prior to our work was that it can be done in TC0, which is a small class, which is a much smaller class than non-deterministic log space. So anyway, I'll come to that in a minute. Yeah. No, edges can come in as well as go out. So in the previous example, we had these two edges going out of the graph, and this edge came in. Correct? So it's both incremental and decremental. Okay? That's in the most general setting. And so let's first take the case that you pointed out, reachability under just insertions. Okay? So this is a particularly easy problem. You can just maintain an auxiliary relation which stores the transitive closure of the graph. So between any two pairs of vertices, whether there is a path or not. Correct?
Also, SNT allowed to change?
So you can, they are allowed to change, but you can, because we are working in the parallel setting, you maintain this for each pair of vertices, for example. So here, so you maintain a binary auxiliary relation T that stores the transitive closure between any two, for each pair of vertices. So I mean, you maintain the transitive closure. And so this is the transitive closure here. The edge 3, 5, which was missing in the original graph, is present because there's a path from 3 to 5. And now if you insert 2, 3, you can update the transitive closure to reflect the change. So lots of new edges are added. And the update formula is very simple. So the transitive closure is suppose either there's a path from x to y, or the path is added once you add the edge u comma v. Correct? So very simple, nothing complicated about this. Just to put things in perspective, we define what a dynamic program P is. So think of it as first order formulas which can update the auxiliary data structure so that you can maintain queries which are, for example, reachability queries and so on. Okay? So we say that P maintains a query if one of the auxiliary relations always stores the query result. Correct? And always means that for all modification sequences starting from the empty graph. Okay? And DINFO is the class of all maintainable queries, all the queries that can be maintained using first order update formulas. And the open question that is the question that has been open for well nigh 20 years is that is reachability in dynamic first order logic, and we answered this in the affirmative. So we confirmed the conjecture that reachability is indeed in dynamic first order logic. This is against both insertions and deletions, not just for insertions, which as we have seen is very simple. So what was known before this about reachability queries in vis-a-vis first order dynamic first order logic? Reachability in acyclic undirected graphs, in both acyclic graphs as well as undirected graphs, was known to be in dynamic first order. And reachability in plane graphs was recently shown to be in dynamic first order also. There are some small classes. So before continuing further, let me admit that the slides come from one of my co-authors, Thomas Zoime, and you will be able to see that most of the slides are his, some of them are mine, and you'll be easily be able to make out the difference between the two. So this one is his slide. So these are subclasses of dynamic first order, quantifier free dynamic quantifier free first order, and dynamic prop, which is first order without quantifiers. And I will not get into the details of this. The reason why he's interested in these classes, in the classes below, are because he can prove some lower bounds for those, which are very interesting, but I will not talk about them in this talk. I might touch upon this result, which was another upper bound, in which we showed that you can do reachability in dynamic AC0. So AC0 is the non-uniform version of first order, and you can do it in dynamic AC0 plus mod 2 gates, plus parity gates. Okay, and that's so that was the thing. This talk we will give an idea of how reachability is in dynamic first order, and so now I come to the results, the main results of this. So in dynamic AC0, very roughly speaking, AC0 is a non-uniform class. In dynamic first order is a logically defined class, and so on. So start quantifiers. So in fact, the way the result went was that we first proved it for dynamic AC0, and then we showed that dynamic AC0 is the same class as dynamic first order. So there are two different parts of the proof. So the results, this is the result of the previous paper. I will only talk about this result in this paper, that the determinant can be done using TC0 computation. TC0, for those who, most of you would know what TC0 is, but just in case. So TC0 is a class of constant depth circuits in which threshold gates are also allowed. You can throw in AND OR gates, but that doesn't change this thing. So threshold gates are allowed, okay? Majority gates or threshold gates. And we can dynamically determine the value of a integer determinant in dynamic TC0, which implies rather straightforwardly that rank is in dynamic TC0 and maximum matching is also in non-uniform dynamic TC0. The other result that I am not going to talk about in this talk is that reachability is in non-uniform dynamic AC0 mod 2, and in fact it is in dynamic AC0 mod p for every p, and some related results about perfect matching. And another result that I will not talk about is reachability in embedded planar graphs is in dynamic first order. This is subsumed by a later paper. So what were the ingredients that went into these results? Very quickly going over them. The first ingredient is that dynamic reachability in dynamic TC0 by a paper of Hesse from 2005, I believe. Another one is the determinant computation by Mahajan and Vinay, and a third component is that iterated integer product is in TC0. This is a well-known paper by Hesse, Allender, Barrington. All three of the papers are quite well known. Of course, the isolation lemma of Murmule, Vazirani. And this is something we introduced, truncated approximation of rational polynomials. And some of the more recent results from the log space community about deterministic isolation in planar graphs and the cut cycle duality in planar graphs. Okay? So I will, for the determinant computation, the first three suffice, and I'm going to talk about determinant computation in a minute. But before that, I will present the results of the other paper also, which are that reachability is in dynamic first order, that is the main theorem. This is via rank of a matrix being in dynamic first order, and some of the other results are maximum matching and perfect matching in dynamic AC0. The ingredients here are that feasibility of a system of linear equations can be, so we can reduce reachability to a feasibility of a system of linear equations, and then we show that rank is in DIN-FO, which is related to feasibility of system to FSLE, and that is through maintenance of a kernel basis of a matrix. And finally, the isolation lemma gives us the maximum matching and perfect matching in DIN AC0. Okay? So just a very quick laundry list of ingredients in this paper. This is not yet published. It's not even on arXiv. We hope to put it on arXiv very soon. So determinant is in DIN TC0. Here we went from reachability to the determinant. So Hesse had proved that reachability is in DIN TC0, and we just took the proof and saw that it generalizes to the determinant using ideas from Mahajan and Vinay. So what is the basic idea behind this proof? So what Hesse does is that he maintains a univariate generating function of the number of UV walks for every pair UV, parameterized on the length of the walk. So you have a generating function in which he just counts the number of walks between u and v of length L and maintains that as the coefficient of x to the power L. Okay. So how does he update that? On addition of edge ij, new walks are added, which consists of a ui walk, some cycles involving ij and ji walks. So you can go from u to I, then follow a cycle from I to j, and then from j to v there is a new walk. This is when you are adding an edge ij. These are the new walks that are added. Correct? Something very simple. Deletion of edge, on the other hand, is the inverse operation on the generating functions, and he showed that both of these can be done using TC0. Okay. So the second component that goes in here is the determinant computation. So the idea behind the MV paper is to reduce determinant computation to counting number of walks in a die. Correct? In some sense. So the proof involves sum of sequences of closed walks. So you take a bunch of closed walks which have some properties, and these closed sequences which are not exactly, so the determinant is actually a sum of cycle covers in a graph. What is a cycle cover? A cycle cover is a covering of the vertices of the graph by cycles, disjoint cycles, vertex disjoint cycles, and closed sequences are a generalization of cycle covers in which you are allowed multiple visits to a vertex and multiple visits to an edge. So the closed sequence definition is carefully structured so that when you sum up over closed sequences, you get back the sum of cycle covers and therefore the determinants. The non-cycle cover closed sequences just cancel out, and you are left with a signed sum of cycle covers. So that is another component that we use. And lastly, iterated integer product, which is a long-standing open problem that can division be done in log space, and this is which was proved to be doable by Chiu, David, Lito, and later on it was generalized to, the proof was made more precise to put integer product and integer division in TC0. So product of n integers of n bits is in TC0, and so is the product of n polynomials. Okay? So with these three components in hand, we put them all together, and the idea is just to maintain a generating function for close. So instead of maintaining generating functions for arbitrary UV walks, we maintain them for close, like Hesse polynomials. So Hesse polynomials, by Hesse polynomials we refer to these univariate polynomials. Instead we maintain generating functions for close, and now we want to compute generating functions for closed sequences of close, and that can be done by taking products of generating functions of close. So it's, in a sense, it's very simple. It's just putting together these three components, and that gives us the result that dynamic determinant is in TC0. Okay. Okay. So now this has two applications. One is the dynamic rank in TC0, which is simple because you just look at the characteristic polynomial of a matrix A, and you plug in and you use Lagrange interpolation to determine the characteristic polynomial, which gives you the rank. Correct? So again, this is very simple. Dynamic maximum matching in non-uniform in TC0. So all this realize that whatever we have said till now is uniform. It doesn't use any non-uniformity or randomness or anything of the kind. It's a deterministic algorithm which runs in DIN TC0. On the other hand, now we use some non-uniformity. So we know that the size of a maximum matching is the rank of the Tutt matrix, is the symbolic rank of the Tutt matrix. Symbolic rank is preserved under random substitution by Schwarz-Zippel, and I mean it becomes the rank of the matrix, and this can be de-randomized at the expense of non-uniformity. So by non-uniformity, you can make by introducing non-uniformity, you can make it deterministic, so to say, or whatever. So that is where matters stood at the once we had this paper. We believed that it should be possible to improve these results. So I didn't mention the result which said that reachability is in DIN AC0 mod 2, but we believe that it could be made uniform, though of course that used the isolation lemma also, and de-randomizing isolation lemma is a tall order. So, but somehow the idea of using determinant for reachability computation is the crucial idea here. So to use rank instead of, so this is in some sense going against the philosophy of the first paper, and so the main theorem we prove is that reachability is in DIN first order. The proof overview is, here's the proof overview. So we look at the question rank and reduce reachability to rank. Rank belongs to uniform DIN AC0. This is something we prove. And finally, we show that DIN FO is the same as uniform DIN AC0. So just to remind you again, circuit class AC0 is polynomially many gates, constant depth, unbounded fan-in. You can also think of this as a CRC-W PRAM for those of you who are more interested in parallel computation with polynomially many processors and constant time. Correct? So DIN AC0 is somehow the analog of DIN FO. AC0 is the analog of FO by Barrington, Nimmermann, Straubing. I guess, I mean, people correct me if I'm wrong. So the first step, reducing reachability to rank. This is quite simple. So the approach is to map a graph G to a matrix B such that ST reachability in G corresponds to computing the rank of B, correct? So when the rank of B is full, then S is reachable, T is reachable from S and otherwise not. Okay? And the B is carefully structured so that it depends closely on the initial input matrix A or the graph G, such that any change in G reflects in a small number of changes in B. Okay? So that this is a bounded first order reduction, and we can compose it in the dynamic sense. So you don't have to worry about composing the reductions. Just suffice it to say that small changes in G will reflect in small changes in B. So the basic idea is simple. The STth entry of A to the I is the number of paths from S to T. Just the basic counting idea. Now observe that this matrix I minus A by n, where n is the size of the graph, is invertible because it's diagonally dominant or whatever So it has an inverse, and the inverse is expressible by this geometric series. Correct? Just like for usual. So this is a well-known fact, and now let us see what does this have to do with reachability. So T is not reachable from S. Notice T is not reachable from S if and only if the STth entry of B inverse is 0. Why is that so? Because the STth entry of B inverse of this inverse is 0 if and only if the STth entry of this sum is 0. And this sum's STth entry is 0 if all the entries are 0, all the entries are positives, nothing cancels out, and that's 0 if there is no path of any length inside G, correct? So if and only if this vector x, which is equal to B inverse of E sub t, what is E sub t? E sub t is the unit vector with t as the, with 1 in t and zeros elsewhere, has x as equal to 0. So I'm just expressing the STth entry of B inverse, correct? And this has a, so multiplying by B inverse, which is invertible, multiplying by B, which is invertible, we get Bx is equal to E sub t, has a unique solution with xs equal to 0. Correct? And so this is a feasible system. This has a solution if and only if T is not reachable from S. So it's it boils down to a feasible system of linear equations, and it can be posed as a rank problem. It's basically rank of a matrix. Correct? A system of linear equations Ax equal to B is feasible if and only if A augmented with B has rank if B is in the linear space of the column vectors of A. So this is a rank question, and we know by what is coming next how to answer rank questions in DIN TC0, in DIN AC0. And B depends very, a single change in A will lead to a single change in B. Right? Okay, so this was simple. Of course, we want integer matrices, not rational matrices, so we multiply it by n, and that just doesn't change anything. Okay, so step 2. So the goal is to maintain rank of an n cross n matrix A with entries from Z. So we want to maintain the rank over rationals or over, yeah. So let's start A with entries from Z mod 2. Okay, and this is all I'm going to present and hand wave to say that it works for any prime and works for Z. But we'll come to that in a second. So we maintain a basis of Z2 to the n, which contains a kernel basis. What is a kernel basis? It's a basis of the kernel of A, which is those vectors A such that A times A is equal to 0. So they map the vectors that are mapped by A to 0 from the kernel of A, and we just want to maintain a basis of Z2 to the power n, which includes a basis of this kernel. And it is, of course, clear that the rank of the matrix A is n minus the number of vectors in the kernel basis. So if we can maintain this basis, then we are done. So now this is a proof by example. So you have a matrix A. You want a matrix B. So this is a basis matrix. You can verify that it is indeed a basis, And now if you take the product of these, you get 3 columns which are 0 and 2 columns which are 1, correct? And and how do we witness the fact that indeed the rank of this matrix is 2? Well, that is witnessed by these 2 ones which are in separate rows, and there is no 1 in that row apart from these 2. So that witnesses that these 2 ones witness the so-called principal components of these columns witness that the rank is 2. Okay. Now, starting from this, let's see what happens. So I think one color is gone, but that's okay. So in comes a 1 in this in the 2 comma third. This one comes in, and now what happens to the matrix? You get a new 1 in A dot B, and now you want to restore the fact that there is just one, that this becomes a principal component, correct? So you want to say that the rank is 3 now because there are 3 non-zero columns with each having a unique 1 in thing. So you add the first column to the last 2 columns, and you get as a result 3 ones, correct? Okay. So this witnesses the fact that the rank is now 3. There are 2 0 columns and which form the kernel basis, and the other 3 form the basis of. So this is indeed the 2 0 columns form the kernel basis. That is the crucial point. Now, so in this transformation, we added these 2. We did these 2 column additions, correct? We added this column to this column and this column to this column. This can be done in parallel. And each addition is mod 2 addition. It can be done in AC0. It's just a 1-bit addition for each pair of entries. So when you add these as a column, see, here we add a 1, but this row also had these 2 1s, correct? So this was not a principal component. This did not witness the fact that this column was not in the linear span of the others and so on, correct? So now once you add these to these 2, these become 0, and so this is the simplest possible case, correct? Okay, now let's take a slightly more complicated case. You have this new 1 appearing here. You get a bunch of, you get 2 new 1s here. And now you can see that there are a number of 1s in this row, correct? So this is not a principal component, and what you do now is to add, as before, these 2 columns containing, so you add this column which contains a 1 in this row to all other components which had a 1. So you add this to this, which is via addition of the corresponding basis vectors, correct? So what happens is, realize that now the principal component of this is gone. This no longer has a principal component, correct? And now 4th column lost its principal component. Choose a new principal component if it exists and apply the same procedure. Okay. So in a sense, this is some very simple addition of some very simple linear algebra. So I will not go into the details of the update rule, but this is the update rule. So the idea is so you have the basis, current basis B, and this is the kernel basis. So I'll just take one rule and explain it just for the sake of completion. So if U is a basis vector which is not a kernel basis vector, such that under the new matrix after the change, so primes reflect changes, U is mapped to the all zeros vector, then move U to the kernel basis, correct? And so this becomes this, and similarly there are these bunch of rules. Okay. So at the end of this, what do we know? We know that, or take it on faith that that we can maintain the kernel basis for mod 2 computation in DIN AC0. And if you go back to the previous slides, you will see that we are not using Z mod 2, Z2 anywhere very crucially. What we have done with 0 and 1, we could have done with any mod P computation. Two mod P numbers are where P is a small prime, is a log n bit prime. So log n bit primes can be added in AC0, and you can take the inverse of a log n bit of a number smaller than a number in ZP in AC0 and so on, correct? So all of that remains in AC0. But now the ranks that we compute are these modulo P ranks. Why should it be the case that the modulo P ranks have anything to do with the integer ranks? And now a simple application of the prime number theorem says that the maximum of those ranks will give you the actual rank, because basically look at the determinant of the largest minor which does not disappear. So okay, so if I may, I have still 10 minutes, correct? Okay, so take a matrix A. Let's just look at the determinant of A, correct? The determinant of A can be divisible by some small number of primes, some polynomially many primes, because it's an n-bit number or a poly n-bit number. So if for any number other than any prime not dividing the determinant of A, modulo P gives the correct, gives a non-zero value for the determinant. Now you apply the same result to all minors of A, correct? And if there is a minor which does not disappear, then that means that the rank is greater than equal to that, the size of the minor, and therefore the thing follows. Okay, so now from DIN AC0 to DIN first order, that is the question, and that requires some amount of logic. Or the logical framework. So it's well known that first order with plus and multiplication is uniform AC0. This is the Barrington-Immermann-Straubing result, and therefore DIN first order with plus and multiply built in is uniform DIN AC0, and we want to show that DIN first order, where these are not built in, it's still the same as DIN first order with plus and multiply. So let me illustrate what do I mean by DIN first order with plus and multiply and the usual DIN FO in this example. So suppose you have an input. If you have plus and multiply available to you, you have available to you the addition tables and the multiplication tables for each of these numbers. Correct? So 1 plus 1 is 2, 1 plus 2 is 3, and for each pair you have this available wherever it's defined. Or modulo P or whatever. So in particular, updates can use arithmetic even from the scratch. Even from the beginning when the graph is empty, updates can be done, updates can use arithmetic, plus and multiplication. On the other hand, in DINFO, you do not have access to plus and multiply from scratch. From the beginning, you don't have them available. In particular, queries like the domain is even is not even in DINFO, correct? So we will, so the focus is on domain independent queries like reachability, where the size of where the query does not depend on how many vertices are there in the graph. As long as the number of vertices, on the number of isolated vertices in the graph, correct? So if you throw in isolated vertices in the graph, it does not change the answer of the query. So in this case, updates cannot use arithmetic, and somehow so Kusha had proved that arithmetic on active domain can be built on the fly in one of his papers on isomorphism, pre-isomorphism. So for example, here, initially these tables are empty. As soon as you add an edge, one element is activated, and now two elements are activated, and now you have you can have entries like 1 plus 1 equal to 2, and these three entries under the multiplication table, correct? So, and these can be built as the computation proceeds, okay? But the problem is, when I is activated, then auxiliary data up to I has to be available, and it is possibly computed by using arithmetic up to I, correct? Only by using arithmetic up to I. So we want to construct this dynamic, we want to simulate a dynamic first order plus and multiply program P by considering an equivalent DINFO P prime. So P prime starts in simulating P on active domains of size n squared as soon as n elements are available. So the basic idea is you accelerate so you run many things in parallel, and you run the simulation for a larger domain in parallel with the smaller one. And so for example, when n things are available, you already start simulating n squared, and that arithmetic to n squared can be simulated by tuples by pairs in dynamic first order, in first order, correct? So we just have to, so when you reach n, you basically start a new simulation for n squared and start inserting in tuples which you have already seen or which are already present in the graph at double the rate, at 4 times the rate or something, correct? So by the time you reach n squared, that you can start using that structure, and hence we are done by this. So in effect, you are, yeah, so let me suffice. Let it suffice. Is the same as, yeah. So now I come to the conclusion of the talk. The main theorem was reachability is in DINFO. There are some corollaries. Conjunctive regular path queries are in DINFO. What are conjunctive regular path queries? So you have a regular expression, and the edges are labeled by letters, and you want to find paths between S and T which satisfy these regular expressions. That is RPQ, that is regular path queries, and conjunctive is another conjunction on top of this. So you can accept those in first order. Also, you can do 2-sat in DIN first order. This is similar to reachability. But this does not imply that all of NL is in DIN-FO, of course. Why does it not imply? Because DIN-FO is not closed under arbitrary reductions. It's just closed under first order, it's just closed under bounded first order reductions. So,
is that example of natural form of NL which is next to
that's a good question. I don't know the answer. But let me think about it. It might be something very simple.
Well, I mean, you pointed out that evenness is not.
Evenness, okay. Okay, thanks. Yeah, so we expect many more applications. There are some very glaring open questions which we would like to solve. One thing which is maintaining a reachability witness. So we know how to maintain reachability between pairs of vertices, but we don't know how to maintain a witness for this reachability. If you ask me for a path between S and T, I would not be able to produce it for you in first order. Similarly, maintaining distances. So we can do reachability, but if you want to find out the distance between two vertices, it's not at all clear how to do that. It's not even, so distances can be maintained in DIN TC0, while for reachability, we don't even know how to maintain a witness in DIN TC0. And maintaining other algebraic properties is, of course, linear algebraic properties is, of course, another question. Why the first two are significant is because that would allow us to give an algorithm for bipartite matching. So bipartite matching would fall in DIN-FO again if we are able to do this in both of these in FO. So that's all I have. Thank you.
So yeah, I have a question. So what evenness? So that's just the
Yeah.
size of the domain.
Just the size of the domain is
But I
enough.
mean, it doesn't change when the query is.
No, if you add an isolated node, it will change, correct?
You only have to add two edges. You also have to add
No, you are not allowed to add edges, add nodes, but I am saying that query depends on the size of the universe and not just on the activated part of the universe. So if you started with some 2n plus 1 vertices and added a few edges, and if you started with 2n edges and added the same vertices and added the same edges, the answer should be the same, while in this case they will be different.
Right. Yes.
So that's all. Yeah.
I was just going to ask about, say, parity problems like parity of the number of paths.
Parity of the number of paths.
It seems like something like your rank computation, the way do it all not true should. I mean, I'm thinking of problems in parity rather than analysis. You see what I mean?
Correct. So from the rank computation, I am not sure whether because
Yeah, it's not clear.
yeah. So, but that's a good question.
Going a little beyond DIN-FO,
Yeah.
is there any possibility that one might be able to consider more general kinds of updates beyond just adding a single edge and deleting it?
Correct. So your paper had that
question
about.
So
Yeah.
in particular, I think it would be nice or more robust if one could do some kind of suitable notion of quantifier-free updates
Correct.
and still be able to maintain it, but obviously I don't know any
So,
good results for that. But
so for example, these regular path queries are in some sense because they are regular expressions, correct? So,
I'm talking about the updates. I'm talking,
oh, you are talking about the updates, of course, of course, of course.
So the question is whether kind of
Yeah, so
going beyond this, because in some settings, a single edge update is appropriate for.
correct, correct.
But in some other cases, for example, when people update the database, they're sometimes updating it using queries in some sense.
Correct,
So,
correct. So that's a good question. I don't know the answer to it. I will think. We did think about this to some extent, but didn't. Yeah.
There are no other questions. Let's thank Samir again.